First of all, I want to say that this is a very broad topic, so my presentation will cover only some of the aspects that relates to verification and validation of evacuation models. But one of the main things that I will discuss today is the need for a protocol for VMV of evacuation models. This work that I'm presenting today is mostly based on some research that I did last year while I was guest researcher at NIST. And I've been working with Erika Kuligowski, Rick Peacock, and Paul Renick. And we were working together on a document in which we were describing and reviewing the current methods to perform VMV of evacuation models and give some recommendations on the process of evacuation modeling itself. So the presentation today will first of all give an idea, a general idea of what is the current state of VMV tests. So what are the tests that are most used today by model testers, and why we need the protocol. So what are the issues associated with the need for a common protocol for VMV of evacuation models. And I will describe some of the what I think are key issues concerning VMV of evacuation models. The first one is the need to having some sort of test to study emergent behaviors. Because when we talk about human behavior, sometimes we don't have only equations. So the models can be agent-based. So what we need is some sort of test that can deal not with traditional analysis of equation-based approach, but also some tests that can fit the simulation on behaviors that can be simulated with the agent-based approach. Then another important topic that I will discuss today is behavioral uncertainty. This is a terminology that we, let's say, created during the work that I did at NIST. We have many discussions on how to call this, but what we call here behavioral uncertainty is the uncertainty affected by that concerns human behavior, so the human factor in evacuation modeling. There are many ways to take into account this, and some people can argue that this uncertainty can fall into other category of uncertainties, but I will describe later the type of work that we did and why we think it's extremely important that this should be included in a VMV protocol. Most of all because this is mostly neglected in the majority of testing procedures that are today available for evacuation models. And the last point is a discussion on acceptance criteria. Of course, I don't have the final answer on what the acceptance criteria should be for an evacuation model VMV, but what I want to point out, the most important point that I want to point out is what are the things that we should keep in our mind when discussing acceptance criteria. And what is being done today on acceptance criteria? Unfortunately, not that much. And what we need to do. So what is the way we should go for? Let's have a look at what is the current state of the art of VMV tests. So for evacuation modeling purposes, we have two main groups of tests, or you can call it guidelines for performing VMV. The first one is a set of mostly verification tests developed by IMO, International Maritime Organizations. And these tests are widely used by model testers, model developers for testing, for verifying their models. I know, for example, in Pathfinder you use some of these tests. The second group of tests that are also widely used, I will say, that are a sort of revision of the IMO tests. There is some overlapping with these tests, but they are modified more for building applications. So one of the issues is that these IMO tests are originally designed for maritime applications, but today are applied for testing, also building evacuation models. So there were some issues with this, and some ongoing discussions on how to deal with this, and there is a German group, this RIMEA group, that has been working on updating these tests and try to make some modification for more different applications, so in the context of building evacuations. And these tests are mostly used, let's say, in the German community. So there is also, I know that there are some researchers that have applied these tests also for evac, but mostly these tests are used for German-based evacuation models. And the group that is working on it, because it's a sort of an ongoing process of revision of these tests, is mostly made by model developers, evacuation model developers from Germany. So these are the two main groups of tests that are used today, mostly for verification. So that's the main problem. When we talk about validation instead, validation, we have an extremely wide span of different experimental data that are used for validation of evacuation models. This creates a lot of problems in terms of, for the user that has to try to understand what is the reasoning behind using a certain experimental data set or not. But we will go through this as well. So one thing that I want to point out here as well is that tests are generally run by model developers. So the majority of the core VMV tests that you can find in the literature are run by the model developers in themselves. And this can create like some debates if they should be only the model developers, if they should be also third parties. But there are also other studies and case studies and tests performed by third parties, mostly research groups, or sometimes the model developers commission to third party to do VMV studies for this. So this is the current state of the art of what we have today for evacuation models. So it's a bit confusing for a user to think that we have so many different different tests and different procedures that are used, because also, apart from the list of tests, there are also some specification in the way you should run these tests that are a bit different between the methods. So the users, as I put in this slide, they're lost. So I really had a hard time to fit all the list of models that are today on the market. I don't know if in fire models you have as many, but in evacuation models, is every day you have some research group or a commercial company that comes out with a new model. So imagine the poor users that is in the position of having on the market 60 plus models, and all these models are validated in a different way. So they have different documentations. There is not a common way to present the results of the VMV performed. So the main core problem is that the user really doesn't know what to do. So what we don't want to risk is that the user is more biased by other factors rather than VMV when choosing a model. So I understand that there are different reasons why a user chooses a model or not, but we actually did a survey on this a couple of years ago, and we saw that model users consider VMV as the first thing they should look at when choosing a model. So the users themselves say this is the first thing we look at, but it's pretty complicated to look at this if the way this is done is different among this infinite list of models. And of course, I know that every single model developers think that this model is the best and advertise it as the best. It's normal. I understand, because that's your everyday work in which you put a lot of effort. But from the user's perspective, it's a pretty complicated situation. So why we need a VMV protocol for this? What is the reason behind this? So as you see, we don't have like standardized procedures. I know, for example, in fire modeling, I'm not an expert of fire modeling, as I guess many people in this audience are. But in fire modeling, I think you have, I've read like some very systematic efforts in comparing like procedures for tests. I mean, the work that Kevin McGrath was discussing for NRC is one example. But for evacuation models, we don't have this. We don't have this standardized procedure. So we have inconsistencies among testing methods. And another issue that is very important is that sometimes some models present different characteristics. So in evacuation modeling, there are a list of submodels that can give the different predictive capabilities to the model that one model can have, one model cannot have at all. One model can be a predictive model for that. One model instead may need simply a user input to give the output that we want for a specific feature. So this is a pretty confused situation for the user. And the other thing is that when we run this, we see this VMV test performed, there is not a common method to consider this result as good or bad. So, and how good is good enough. So we really don't know when results are good and when results are not good, because there is not, at this point, the evacuation modeling is a younger field of research compared with fire modeling. So there is not a common acceptance criteria. There are no common acceptance criteria for which we can say this result is good, this result is not. So what we did is a joint effort. So we put together people from NIST and people from Lund University, and we had some sort of different background on this, because me and Erika, we are mostly, Erika Kuligowski, we are mostly evacuation modelers. So we have been dedicating a lot of time testing many models, while Rick and Paul have worked a lot with VMV for fire models, so they had also the other expertise for this, the other side of the expertise. And my colleague in Sweden, Daniel Nilsson, is an experimentalist, so he's a pure experimentalist for evacuation experiments. So we joined our forces and we tried to address some of the questions that the users often do. So, and this document that you see here is the result of this joint effort. This is a NIST technical note. So, many times it happened that model developers ask me or other people that are in this field, what is the reference that we should use to perform VMV tests for evacuation models? And if they think that we now have the solution for this with this document, the answer is no, unfortunately. I am not in the position myself, even with this group of, let's say, experts of this subject, with our only effort to define what is a final guidance for the performance of VMV of evacuation models. But from our side, we brought something new that has never been done before. So we've done a sort of a systematic review of the IMO tests. So these tests that are the most commonly used today for the VMV of evacuation models. We have discussed what are the features that I would say, a minimum list of features that should be tested within the model. And this is based on the work that Erika Kuligowski did here at NIST, because she categorized in a very structured way what are the features that are inside evacuation models. And then another big issue is that these tests are generally very scattered. When you see this IMO test procedure, or also this RIMEA procedure, they really do a very good job for testing certain components, but it's a bit blurry for an average user to understand what is the logical flow of testing one feature instead of another. So what we did is to borrow the categorization that Steve, that is sitting here, did for the different core components that are within evacuation models. And then we structured this in a systematic way, in such a way that the user can, okay, I need this model for this specific core component that is of primary importance for me, for my study. So, and you can have a look at all the tests that have been done within the procedure, within that core component. So this is another new idea that we brought in this document. And then we actually, after reviewing the IMO test, we gave some suggestions on what can be possible verification tests. Of course, there are many ongoing debates within the evacuation modeling community. So what are the features that should be tested, in which way they should be tested. But we gave our point of view as researchers that is completely unbiased. So we don't have any reason why we should say this should be included in the model, this should not be included. So, and depending on the field of application, because as I said before, the main problem with the IMO tests is that they're specifically designed for maritime applications, and they're used also for building application. And this creates some controversial points in to which extent you can use something that is verified and validated with tests for one specific field to another field. Of course, I know that model developers do an effort to extend the IMO test to also other type of tests. I mean, this has been done, but this is something that we have addressed in this tech note. And the last part that is a topic that has surprisingly for me never been addressed in evacuation models, is the study of what I called the behavioral uncertainty, so the human factor, how the human factor impact the results of evacuation models. And we will see this as it is done today. Most of the evacuation models present distributions, so present some stochastic variables or different methods to account for the fact that people may behave in different ways, even in similar conditions. But as for today, before this document, there was not a method to study this. So, and we will see that there was a pretty straightforward way to study this, the impact of this, that probably had some limitations. So we did some sort of critical thinking on this to try to address this problem. So here, as you can see, I list what are the main core components that we have included in this VMV protocol. And as you can see, I mean, for those of you that are experts of evacuation models, of course, you know that there are other type of subcategorization that you can do. Actually, this is pretty much the same as what Steve did. I modified with Erica. We decided to modify the second aspect to have a broader way, because originally it was more travel speed in the classification, but we wanted to call it movement and navigation to have a broader approach on what kind of tests we can insert here. But the idea is that you model user, that you are lost because you have 60 models to choose among. You go to this list, you know what is the factor that has more impact for your study that you have to conduct, and you know exactly what tests have been done for each of these components. So this will make the life of an average user that have to choose among models, or have to evaluate the model that is chosen and want to see what kind of efforts has been done for VMV in a pretty straightforward way, rather than the a bit blurry sequence of tests as they are presented today in IMO and this RIMEA testing procedure. And the second issue that we have raised and we have addressed is the fact that tests, as they are presented today for VMV, they are also blurry in terms of what the tester should do. In terms, there is not a very structured way of looking at what are the sequence of steps that the model tester should do. So we put together a very simple sequence of steps that the model tester should do when performing a VMV procedure. So having a look first of the geometry of the scenario that you're taking into consideration, then the scenario itself, the evacuation scenario, then what are the results that you expect. So, and the result that you expect cannot be simply, for example, an evacuation time, but it can be if you're studying other things like congestion, or you want to study exit choice. So don't think this only as numbers. These are not necessarily numbers, because we use also agent-based approach. So the results are not necessarily numbers. And the fourth point is the test method. So what kind of test methods we are using for evaluating the results that we get. It should be qualitative, it should be quantitative. What type of quantitative method, what type of qualitative method? Are you using a visualization tool for evaluating your results from an evacuation model? Are you not? So this is the fourth point. And the fifth point that actually came from a very interesting comment that I got from Steve when we were working on this, is the fact that sometimes you really need to be extremely detailed when you have to present your results. And the problem is that the poor user can face different type of documentation with different type of information. So if you tell instead to the model tester in a very structured way, okay, in the fifth point, the action that the user of this test, so the model tester should do to document this, this, and this, in the way you have run this, what type of different variation of your test you need to do independence of certain type of models that you have. I make you a very simple example. So there are certain tests that may work pretty well for certain models, but for other models depends on the assumptions that you use when you run the test. The classical example is that if you have a straight corridor, a straight line, and if you have a model that simulates movement in a grid, depending on this corridor, if it's straight on the grid or if the grid is rotated on the corridor, you can get different results in some models if they're not properly verified. So this is something that we discovered in one model. So, and when the model tester was running the test with a simple corridor in the parallel grid, with the grid that was in parallel with the corridor, was not looking at this. But the kind of critical thinking that we should have is to try to cover as more models as there are on the market and that use different assumptions. And nowadays, it's pretty structured what type of assumptions the model use for evacuation, if they use like a different type of network or if they are continuous models. So we know this. This is pretty categorized in evacuation modeling. And in relation to that, give information on the type of, let's say, variation of the test that you should do depending on the model that you have. So this is the fifth point of this. So the other issue that we have here is when evacuation models are actually predicting something. So this is one of the main questions that we had, because you have sometimes certain data sets that are used to develop a theory, or you have a theory and then you plug into a model certain data. So the reason is, the problem is sometimes you just plug into the model the results that you want. In evacuation model, this is extremely straightforward. I think in fire modeling, in a certain way, I can do an analogy on when you like are assigning certain properties for certain materials, or you're giving specific data that you already have. But if you have a consolidated theory for this, what you're using is just plugging the data in the model. Sometimes in evacuation models, you have different theories to explain the same behavior. So which one is the right theory? So, and which one are the right interpretation of the data that you have? So plugging the same data in different models that use different theories, you get different results. So this is an issue, and this should be addressed. And the other thing that should be addressed is what type of input specification you have to give to the model to get certain results. So to what extent the model is actually predicting something, so it relies on its own theory, and to what extent instead the model is fed by the data itself. So without the data, you cannot get any result. And in evacuation model, this is a big issue. So for this, for the fact that we have different theories to explain the same behavior, we have identified something that is in between verification and validation. I mean, you can, of course, argue about the naming, but we call it verification of emergent behavior. So the ability of evacuation models to qualitatively produce results that reflect the current knowledge of human behavior in fire. And the problem of this, that there may be different theories that differ substantially to explain the same problem. And the question is, what are the acceptance theories? So the first step should be in a protocol to review what theories are today used within evacuation models and which one are what we consider today the truth, or less the truth, or less valid. And also, this is related to the modeling approaches that we have. So in certain cases, we don't even have experimental data to reproduce certain behavior. So what we do is to use ideal cases, so simple evacuation scenarios that are based on, the results are in which we can study the results based on evidence or simple mathematical equation. And this is an approximation that we are forced as today, because certain problems in evacuation modeling are simply a big question mark for us. So we gave some suggestion of ideal test cases that can be used in this tech note for different type of features that you see listed here. And the other main issue that we are addressing in this tech note is the issue of behavioral uncertainty. So as you see, the first 3 points here, I mean, there are many types of classification for uncertainty here. I just borrowed the one from Anthony Emmons and Kevin McGrath. And I had a very interesting discussion at the time I wrote this with Anthony Emmons, because he was telling me, okay, but probably you can insert that human factor in one of the other uncertainty, but we wanted to keep this isolated because we want in a test procedure to account for the fact that the human factor can be a principal source of uncertainty. I make you an example here of what are the classical 3 types of uncertainty for evacuation. There are many examples for fire modeling, but for example, uncertainty can be experimental measurements associated with experimental measurements. So for example, the pedestrian tracking techniques that you can use to measure the speed of people in a corridor. When you talk about the input uncertainty, we are talking about, for example, the distribution that you use for walking speeds. And the calculation method is the intrinsic uncertainty. So basically what maths you are using or what agent-based approach you are using to simulate people movement. Behavioral uncertainty instead is this. So if you try to evacuate the same building with the same people starting the same places on consecutive days, you can get different results. And this makes the life of a modeler very hard. And this is a problem that people try to explain in a different way. I took this quote from Newton to explain that I can calculate the motion of heavenly bodies, but not the madness of people. So, but this should not be considered as an intrinsic limitation of evacuation models, because what I want to point out here is that the evacuation model uses account for people madness, the way Newton defined that. And the thing is that most of the models are not deterministic. So if you use distributions for the inputs and results, you can have a method to tackle this issue. And the thing is, why do model developers use distribution? So, and there are two theories on this. So if there is one, let's say, theory that says that the problem is that the human element can never be predicted. So we have to give up on this. And so assess experimental behavioral uncertainty is not possible, never be possible. But since we are researchers, I'm more tending to the second point. And the problem is that we still don't know what are the intrinsic variables that affect human behavior. I've been working with psychologists, and I've seen them that they go through the really intrinsic properties of people, intrinsic characteristics of people to study what then cause certain behavior. So if we can go deep, so imagine in some years we can study why you do something as a person, then you can treat experimental behavioral uncertainty as something that we can quantify. So the testers, do they account for the people madness invalidation? That's a big question, because sometimes it's very hard because we perform a validation study with a single experiment. So you have a single experiment, and then you have a set of results generated by a distribution of input. And what is the overlapping that you see in this? You actually, sometimes you don't know, because you don't know if this is an average case or if it's a very worst case scenario, what you're observing. So, and the problem is that we have very scarce data on repeated experiments. So I don't blame the model tester. It's because of the current state of the art of human behavior in fire. And another issue is the circular validation. So if you use certain data for calibrating a model, and then the same data are used for validation, you will get perfect results. So this is something that should also be addressed when studying this. And the last point that I discuss here is about the runs for each scenario. So we have sample data that are taken from distributions, but we don't have a method today in this testing procedure to study how many runs we should run. So I get bazillion of questions from a lot of users that say, how many runs should I do? And 50, 30, you have like these magic numbers every day. And what are our results? So the question is, the users are lost because there is nothing that tells them what to do. And there are now instead methods to do this. So as it is in IMO, you basically run 50 runs and you say, okay, I'm accounting for the behavioral uncertainty. And this is a very arbitrary method. So there are different steps, and what is done now is to try to study with a bit more systematic mathematical way using vector mathematics. We basically, with Paul and Rick, we borrowed the methods for fire simulation, and we use this for studying the convergence of curves. So there is some method to study this that can be included and discussed in a protocol, but it's not done today. And finally, the last point, the very last point, is about acceptance criteria. So who basically should define this criteria? Should be the model developers. There are some model developers that gave suggestions for criteria, but it should be international organizations, regulators, users. And should this depend on the intended use of the models? Probably yes. And what results should be taken into consideration? Worst, best predictions. So these are all things that are not addressed in today's procedures. And this should be minimum criteria, or should we aim at certifying models in such a way that then the user can have a certain degree of confidence we're using it? So all these questions that I put here, there are actually 21. I counted them. And I'm very interested to listen what are the different views from people that work with the development of software, people that are users, or regulators, researchers, to listen what you think. And if this broad debate can feed a better development of a protocol, at this point we are trying to bring this to ISO. I've been in the last ISO meetings presenting this issue, and I got positive feedback. And next month in Sydney, in the next ISO meetings, we will discuss the need to have some sort of subsection for VMV for evacuation models. So if you are willing to contribute to this, just ask me and tell me how to do this, and I will be very, very happy to hear from people that wants to contribute with this. So thank you. This is just an acknowledgement to my co-authors of the tech note, so thank you.
Thank you. We have time for just a couple of questions if there are any in the audience. Any interested parties willing to volunteer for validation? Yes, Richard?
I think the idea of certified model sounds wonderful. It seems like it would be
I'm sorry, I cannot hear you. It's a bit...
the idea of having a certified model. Can you hear me? All right.
Yeah, great.
I like the idea of having a certified model, but it seems like that'd be really hard to accomplish with all the different, all the different countries that use this have their own way to certify a model. So how could we go about that?
At least having a starting point of a common procedure built in ISO will be a starting point. So that's my point. As it is now, we really have feedback. I hear continuous debates on this in social networks, in conferences, that people are willing to contribute to this, and there are individual researchers that try to look at this, or model developers that look at this. And what I say, why we don't join our forces, why the researchers at NIST, Lund, and the German groups, and here the companies that work with this cannot put together their ideas and work towards at least having a common method. Because this is beneficial for everybody. It's beneficial for the users that will have a better idea of what the model can do. And it's beneficial for the developers, because for you it's good if you have the chance to show what your model can do in a very structured way. So this is the main point of this presentation. Of course, short term, this is not something that can be accomplished short term, but getting going with this sort of debate and bringing this to feed some sort of standard, like in ISO, for example, but there can be other platforms. This is the one I'm involved with, but there can be other platforms for this.
Okay. Okay, thank you. Any other questions?
Yeah.
Here you go.
You talked about having a structure for testing, and one of the points that you made was about, thank you, about expected result. Could you elaborate on this? Is that, does that pertain to the theory? Is that what you talked about with the rotated grid?
The problem is that sometimes when you talk about results, when I've been talking with people involved mostly in fire modeling, they have in their mind numbers. In evacuation, it's not only numbers. Sometimes it's behaviors, it's choices. So it should not be, in a standard protocol, should not be something blurry. So you should not say congestion as it is. What does it mean, congestion? The flow rate, or it means the density, or it means like, so the point is that it should be very, very, very structured, the type of output we are talking about. And this is not straightforward for evacuation modeling. For fire modeling, probably, I'm not an expert, I repeat, surely here there are way more experts than me on this, but my feeling is that it's way easier to define what an output is in fire modeling compared to what an output is, and what is the result we are talking about in an evacuation model.
All right, well, thank you. Thanks again,
Thanks.
Enrico.
Thanks.